Alright, now that we know how to describe an LC circuit, we're going to now put back the element of resistor, R. So we have a more complete circuit called an RLC circuit. We put everything in series. There is a resistor, there is an inductor, there is a capacitor. This is more realistic because in a real world, there is no such thing as a pure inductor without any resistance. You always have a little bit of resistance. Okay, so what happens when you have an RLC circuit? Well, once again, for simplicity, let's say at t equal to 0, the moment you close the switch, the capacitor is fully charged with a lot of charge on both plates, but there is no current. Okay, the energy is completely stored in electrical form. Now, of course, after you do that, after you close the switch, you're going to form a current, right? It's just like the LC circuit, except this time the current also has to pass through a resistor. And what that resistor does is then, of course, it will turn part of the electrical energy into what? Into heat. Okay, as a result, energy will be gradually dissipated in the form of heat. So you no longer have conservation of electromagnetic energy because the capacitor will turn electromagnetic energy gradually over into heat. So, qualitatively speaking, if the charge as a function of time can be drawn without R, if it can be drawn like this, okay, you know, it will be a pure sine or cosine function, right? With no decay, okay? It will be just, you know, there's not going to be any drop in magnitude over time. It's going to stop. It's going to keep oscillating forever, right? If you don't have the resistor, right? What I want to know is qualitatively, when you have a resistor, how is this curve going to change over time? Okay, first of all, with the resistor, energy will eventually disappear from electromagnetic form and turn into heat. So eventually, all oscillations will be diminished and Q will become 0. Okay, so it is not going to keep the same amplitude forever. It's going to rather decay. The amplitude is going to decay. Okay, that's one thing. Another thing is that the presence of the this resistor means that some of the EMF some of the voltage drops has to be spent on the resistor to overcome its resistance, and therefore, if everything else is the same, the charging and discharging current will be less than before. In other words, less than the case without R. So overall, you expect a smaller current, and that is going to make the charging and discharging process slower than before, right? Because you know it's going to take longer time to fully charge the capacitor because you no longer have the same amount of current. Okay, so therefore, you expect not only the charge is going to diminish over time, but also it's going to take longer time for repeat one oscillation. So you expect longer period. Okay, so these are the two things: longer period and diminished amplitude. So you expect something like this. All right, this is qualitatively how Q would change over time. Now, let us study the full equation to see how we might describe this curve. Okay, to do so, let's write down the Kirchhoff's rule equation this time by adding simply one more term, okay? You know, just one more term. So what do we have? We have this guy, okay? So VL, next one, actually this VL and VC, and then VR, you just add them all together. You should get a constant, you get 0 because there is no EMF. Okay, so the first term is L times the second derivative, right? The next term is VC, which is Q over C, and the next term R, which is VR, that's IR, so it's R times the dQ dt. Okay, dQ dt is just I. Right? That should be equal to 0. But you see, that is mathematically also analogous to a mechanical system. In the case of mechanical oscillation, if you do not have any damping, then of course the oscillation will go on forever, just like a complete LC circuit without R. But in reality, there's always some damping mechanism or some friction, and frictions comes in many different forms. But in particular, if we study a simple type of friction, linear friction, in which the force of friction is linearly proportional to the velocity, okay, then in a mechanical system we would have F equals ma, and the the force is not only negative kx, okay? There's one more form, minus b dx dt. dx dt is v. This is the damping force, okay, or friction. It is a linearly, it's a friction that's linearly proportional to the velocity. Not all frictions are like that, but with this particular type of friction, we have a good analogy between these two cases. So, restoring force from the spring and friction. That's the total force, equals mass times acceleration. Mass times acceleration, which I can always rewrite. Okay, this equation I can always rewrite. I can move both terms to the other side. I get m d squared x dt squared, right, plus kx, and then plus b dx dt equals 0. Right? So you have the electromagnetic equation here, and you have the mechanical equation here. Now, look at the analogy. Okay, again, x is replaced by q, right? M is replaced by L. K is replaced by 1 over c, as we expect before. But what else? Well, B, the damping constant, is replaced by what? By the resistance. Okay, so the resistor is equivalent to the form of friction in the mechanical case, which makes sense energetically, because energetically, friction turns mechanical energy into heat in the mechanical oscillator, and here resistor turns electromagnetic energy into heat. Okay, so these two correspond to each other. That tells us that when we go back to the table of correspondence, we should add one more entry, B. Okay, that is the damping constant now becomes R, the resistance. That completes the analogy between electromagnetic and mechanical oscillations. So what do we need to do now is we need to solve this equation. Okay, we need to solve this equation on the top. Now, some of you may know how to solve this equation, or may have actually done so in the mechanical case. But I'm assuming that nobody has done that before. So let's try to solve this equation. Okay, we expect the solution to look something like that. Okay, to look something like that. Now, what do we get? Mathematically, this type of equation is rather simple to solve. Even though you have a second derivative and first derivative, all you have really is the sum of a whole bunch of linear terms. There is no such thing as q squared or sine q, nothing like that. Everything is just q to the first power. Okay? This particular equation is up to second order. So we call it second order linear differential equation. It's also homogeneous, meaning that there is no source term, there is no EMF here. Okay, it's just equal to 0. So we have a homogeneous linear second order differential equation, which sounds like a mouthful, but actually it's quite simple to solve. Mathematically, all you have to realize, as we've done that numerous times before, is that all these different order derivatives, here is a second order, here is a first order, here is a zeros order, they all add up to a constant, which in this case is actually 0. And that means that they should all have the same functional form. They should all depend on t in the same fashion. That's how they add up to 0. And the only way to make that happen is to choose an exponential function, right? So assume, okay, that q goes like e to the power lambda t. Okay, you know, I didn't use an equal sign because otherwise you have to put a constant in front of it. That constant doesn't matter because it's going to be dropped here, here, and here. Each term is a constant, so it's never going to show. It's never going to show here anyway. I'm more interested in lambda. Okay, I'm more interested in lambda. What is lambda equal to? Well, all you have to do really is to plug this trial solution into here to see what you get for lambda. So what do we get for the first term is L times second derivative. That's lambda squared. Okay, there is also an e to the power lambda t. I'm not going to rewrite here. I'm not going to re e to the lambda t here. I will just put it off a little bit later. Okay. Now look at the next term. 1 over c. Q is, and you take a time and you just have to plug it in, and you also have e to the power lambda t. So I'm gonna write it a little bit later. E to the power lambda t. Okay. Now the next term. What? R dq dt. R dq dt. When you take dq dt, you get a lambda, and also e to the power lambda t. So there's an e to the power lambda t in every one of these terms, which I'm going to take out. Right? You get 0. You see that? Okay, now that's wonderful because this guy changes with time, and the other side is 0. So the only way to make it happen is to make this equal to 0. And look at what we just did. We just turned a differential equation into what? Into an algebraic equation for what? For lambda, right? This in fact is a quadratic equation for lambda. Okay, it's a quadratic. We have turned a second order differential equation into a quadratic equation. So let's solve for lambda, shall we? Okay, using the familiar formula for lambda for quadratic equation. So lambda, there are in general two solutions, 1, 2. Let's see what is that equal to. Okay, negative b plus or minus b squared over square root of b squared over 2a over 4 minus 4ac, right? Okay, b is what? Okay, here is the quadratic term, here's linear term, and here is the constant term. Okay, so b is the constant in front of a linear term because it's ax squared plus bx plus c, right? So this is r, right? And then plus minus the square root of b squared minus 4ac, so r squared minus 4ac, 4. A is the constant in front of the square terms, is L. Okay, c is a constant term, but here is 1 over c really, so it's divided by c, right? And then divided by what? By 2a. A is L, so it's 2L. Right? That is the most general solution. Now, take a close look at this solution. As a matter of fact, there are 3 possibilities depending on what happens inside that square root. We have discussed that long time ago when we studied the solution to quadratic equations. This is the discriminant, right? Whatever happens to the discriminant will determine the outcome lambda. There are 3 cases when the discriminant r squared minus 4 delta is r squared minus 4L over c. It can be greater than 0, it can be equal to 0, it can be less than 0, right? These are the 3 possibilities. Okay, if it's greater than 0, right, then you have a positive value under the square root, which means this whole thing is positive. Okay, then you have r plus or minus that, right? R plus or minus that, and oh, sorry, I forgot a negative sign here. I'm sorry, negative b, right? Minus b. Okay, now you got 2 possibilities, a plus and minus sign, but you get a real number here. Okay, so it's negative r plus or minus a real number. The magnitude of that real number is square root of r squared minus 4L and c. So this magnitude is less than r, right? So my question is, can we pick both the plus or minus sign, or can we pick up only one side? Well, remember, the magnitude of the next term is less than r. So if you pick a positive sign, okay, you pick a positive sign, overall you will get a negative value for lambda. And if you put a negative sign, of course, you still will end up with an overall negative sign. And that makes sense because, remember, the expression is e to the lambda t. I want lambda to be negative from physics point of view. When lambda is positive, that means q will grow exponentially over time. Does that make any sense? No, it makes no sense, right? How can q grow exponentially? Lambda has to be negative. And no matter whether you choose a positive or negative sign, you will end up with a negative value of lambda, which is good, which means both of these 2 roots will be useful. So you have 2 solutions, okay? One is e to the power lambda 1t, the other e to the power lambda 2t. Both lambda 1 and lambda 2 are negative, but whichever you choose, or you can choose both, anyhow, you end up with exponentially decaying function, okay? Exponentially decaying function of time. So q as a function of time will go down. Okay, it's going to go down like that. Exponentially decaying function. There is no oscillation whatsoever. Does that surprise you? Well, it might be surprising, but really, if you come to think of it, it may not be that surprising, because after all, this is when the discriminant is greater than 0, and that only happens when r is large enough, right? R has to be greater than the square root of 4L over C, right? Okay, so you have large R. That means large resistance. The resistance is so large, okay? The resistance is so large that so much energy is dissipated into heat as the current starts to flow, then there is no chance for oscillation to sustain, okay? So it just simply just drops monotonically to zero, all right? Q just drops monotonically to zero. There's no oscillation. There's too much damping going on. And in mechanical case, we have a similar situation. We call it overdamping. We call it overdamping. Same thing here. We call it overdamping. There is no oscillation. The resistance is so large, it just simply kills off the oscillation. All right. The second case is when discriminant is equal to 0, so R squared equals 4L over C. Okay. Now, if that is the case, you just left with one choice for lambda, which is negative R over 2L. It is a negative real number, so you will still get, okay, you will still get something like, something like that. Okay, it is still a monotonically decreasing function of time. There is no oscillation. So both overdamping, that is delta greater than 0, and the second case, which we call critical damping, by the way. Okay, critical damping. There is no oscillation. R is still pretty large. Okay? In fact, we call it critical damping because there is barely enough damping to stop the oscillation from happening. As a matter of fact, if R squared is less than 4L over C, which means delta is less than 0, then you will have oscillation. Look. If that is the case, you're going to end up with a negative value under the square root, right? A negative value under the square root. That means what you have here, the whole square root expression is not a real number anymore. It is an imaginary number, right? It is an imaginary number, so you're looking at something like that. You're looking at lambda equals negative R over 2L. I'm taking the first term out. Plus or minus what? This thing under the square root is now negative. Okay, what I'm going to do is I'm going to reverse the order of 4L over C and R squared. So I'm going to put 4L over C minus R squared. I'm going to take them out. I'm going to reverse the order. Of course, there will be a negative 1. Now, you know the square root of negative 1. What's that? That is the imaginary number I, right? Okay. Don't forget I have to divide by 2L. I have to divide this whole thing by 2L. Okay, let me clean things up a little bit. The first term, negative R over 2L. Then plus or minus. I am going to, okay, work this out a little bit. Now, negative square root, negative 1, that's just I. Okay, this thing here, let me move the 2L into the square root. That becomes 4L squared. So you have what? 1 over LC minus R over 2L squared. And this expression, this whole thing, is a real number. I call it omega. Okay, let me call it omega. So now I have negative R over 2L plus minus I omega. This is the expression for omega. Now, remember our whole solution is e to the power lambda t. So our solution will look like this. Q should go like e to the power lambda t. Lambda is right here now. Okay, so it's negative R over 2L t. And then, don't forget there is also e to the power plus or minus I omega t. So, then e to the power plus or minus I omega t. What is this? Huh? What is this? Well, anybody who knows the Euler formula, remember the Euler formula? Anybody who knows the Euler formula knows that e to the power I theta is cosine theta plus I sine theta. That's the famous Euler formula. You can show that by expanding each of these terms into power series, and you can match the real part, imaginary part on both sides. You see they're equal. With the Euler formula, this exponential is now really equivalent to cosine omega t plus or minus I sine omega t. This means we have oscillations cosine sine omega t. Okay, so overall, what I have here is this type of function. You have a sine or cosine omega t. There is oscillation, but the amplitude of oscillation is now modulated by this factor. E to the power negative r over 2l times t. So as time passes by, you're going to diminish. Okay, the amplitude is going to diminish. So now we're going to have an oscillation like that. We have an oscillation like that. Like that. Okay? There is an overall profile or envelope, and that function is e to the negative r over 2l times t. Okay? So that's q, and that's time. And what about the oscillation frequency or angular frequency? Well, it's omega, and omega is equal to the square root of 1 over LC minus r over 2l squared. Take a close look. This is less than the square root of 1 over LC. See that? What is the square root of 1 over LC anyway? That was the angular frequency of what? Of the LC circuit without the resistance. Now we said that with the resistance, we expect omega to be a little bit less. It was the oscillation to slow down a little bit because of the resistance, right? And that indeed is true. You see, with R here, you have a small level of omega. Okay, so the full solution should look like this, with all the constants added in. Q equals Q maximum e to the power negative r over 2l t cosine omega t plus final. You should expect a full solution like that. This is a damped harmonic oscillation, just like we would expect in a mechanical analogy. Okay, in a mechanical analogy, when you put in a linear damping force, you're going to get a damped harmonic oscillation. It's very similar here. And again, the key feature of this oscillation, as compared with the free LC oscillation without any damping, is actually two things. One is you have a decaying amplitude that is controlled by this term, okay, or this envelope. The other is you have a smaller amplitude. I mean, you have a smaller omega, which means you can slow down. Okay, the period will be greater, the frequency will be lower. In that particular case, of course, going back to here, it only works when the discrepant is less than 0, right? Or when this is the, this whole thing is a imaginary number. So that's a smaller r. Okay. R is small enough that there is not enough damping to kill the oscillation instantly. So you're going to have oscillation gradually diminish to 0. We call it underdamping. Very analogous to the mechanical case. Okay, the underdamping, of course, is of the most interest to us because there's actually an oscillation here, and this is what the profile looks like. Now, it makes sense that you have an R over 2L here. If R is large, you're going to quickly decay to 0 because you have, with large R, a lot of energy is turned into heat on the resistor. And what about L? Well, L measures the ability to resist any change in current, right? If L is large, the current is not going to diminish quickly over time because it's difficult to do with a large inductor. So that means when L is large, it's going to take a long time for the for the current to, or the charge to decay to 0. Okay, and this formula also makes sense. You see, when R equals 0, you go back to 1 over square root of LC as expected. When R gradually increases, you find omega should decrease, okay, because there is more damping to make the oscillation slower and slower and slower. And at the critical moment, critical point when the second term equals the first term, omega is 0, you no longer have an oscillation, and you go back to what? To critical damping. Okay? And when this term is even greater than that term, that's even worse. Then you go back to the case of overdamping. Okay, now at this point we have studied the electromagnetic counterparts of free oscillation, which is LC circuit, and damped oscillation, which is what? Which is an RLC circuit. But if you recall, in a mechanical case, we also studied what? Forced harmonic oscillation, right? Because in the real world always have damping, so you cannot expect the oscillation to just maintain itself forever. There is no such thing as completely free, undamped oscillation. So you have to drive the system. So later on, in fact, in the next chapter, we're going to see what happens if you want to maintain an electromagnetic oscillation in an LRC circuit in the presence of resistance. And the way to do that is by installing an EMF here. Now, this EMF is not going to be a constant EMF, because if you look at the mechanical analogy, you have a spring mass system, right? How do we force to oscillate? We don't apply constant force, do we? Right? If you apply constant force, it's going to compress the spring, and that's it. But what we do is we're going to grab the spring, we're going to shake it back and forth with a driving frequency, right? So similarly, we're going to put in an EMF which itself varies back and forth, back and forth, back and forth with its own frequency. And we can see what happens when the system is powered by such an EMF. You will have, again, no longer a free damped oscillation anymore. Rather, you're going to have a driven or forced electromagnetic oscillation. That will be the subject of the next chapter.